Okay, so chemical changes. Huh. It's a pretty big deal, wouldn't you say? Like, it's kind of at the heart of GCSE chemistry, right?
Yeah, absolutely. Chemical change, I mean, they're everywhere, really, aren't they? It's all about how substances change, how they sort of do their thing and react with each other.
I mean, you're talking like how a cake bakes, or how metal rusts, or even like what happens when you take an antacid.
Yeah, all that and loads more. It's like fundamental to understanding, well, pretty much the whole world, isn't it?
No pressure then for this deep dive. So we thought we'd focus on three big areas, right? The reactivity of metals, for one.
Yeah, that's a good one. Some metals, they're like ready to party at the drop of a hat, while others, well, they're a bit more chilled out. Then there's reactions of acids, which can get pretty lively sometimes.
Fizzing and bubbling and all that good stuff. And lastly, we'll tackle electrolysis. Sounds a bit intimidating, doesn't it? Using electricity to split things apart, all that.
Yeah, but it's actually pretty good when you get down to it. So those are our three biggies for today. And trust me, if you can wrap your head around these, you'll be well on your way to cracking chemistry.
All right, let's do this thing then. First up, reactivity of metals. I remember struggling with this bit back in school. So what's the deal? What makes some metals super reactive and others not so much?
Well, at its core, it's all about how easily a metal atom loses electrons. You know, those tiny negatively charged particles that whiz around the nucleus. Some metals are practically throwing those electrons at anything that comes near.
And that makes them reactive, losing electrons.
Exactly. It's all about that tendency to form positive ions. The more easily a metal loses electrons and forms positive ions, the more reactive it is.
Okay, and I'm guessing this is where the reactivity series comes in.
You've got it. It's like a league table of metals, ranking them from the most reactive to the least.
So at the top of the pops, we've got the real party animals, right?
Yeah. You got like potassium, sodium, lithium. Those guys are seriously reactive. Throw them in water and whoosh, stay back. They react really quickly with water, releasing hydrogen gas and all sorts.
Okay, so water's like their dance floor. And what about those further down the list?
Well, as you move down, things get a bit more mellow. Magnesium, for instance, it reacts with water too, but not as violently. Then you've got zinc, iron, they're even less reactive. And copper, well, it pretty much sits there like, not really interested.
Copper's the wallflower then.
Pretty much. It hardly reacts with water at all. And, you know, we can also throw hydrogen and carbon into this reactivity series, even though they're not metals,
Why is that?
because they play a big role in how we extract metals from their ores, which we'll get to in a bit. It's all connected, really.
Right, so we've got this reactivity series, but what does it actually mean in terms of reactions? Like, what can a more reactive metal do that a less reactive one can't?
Ah, that's where displacement reactions come in. It's like a chemical showdown where the more reactive metal swoops in and kicks the less reactive metal out of its compound.
A bit ruthless, eh?
Sort of. Say you've got a solution of copper sulfate, which has copper ions in it. Now, if you add some iron to that iron being more reactive than copper, the iron will literally displace the copper, forming iron sulfate and leaving copper metal behind.
So the iron's like, move over, copper. This is my spot now.
Yeah, you could say that. And it's not just metals. This kind of displacement reaction happens with halogens, too. You know, those elements like chlorine, bromine, iodine. The same principle applies. The more reactive halogen will displace a less reactive one from a solution of its salts. It's a bit like chemical musical chairs, with the most reactive element always grabbing the best seat.
I like the analogy. All right, so we've got this reactivity series. We know about displacement reactions, but how do we actually get these metals in the first place? They're not just lying around in their pure form, right?
True. Most metals are found combined with other elements in ores, usually oxides, sulfides, things like that. So we need to extract them. And guess what plays a key role in this?
Let me guess. The reactivity series.
Bingo. For metals lower down the reactivity series, think iron, copper, lead. We can extract them by heating their oxides with carbon.
So carbon's like the metal rescuer?
In a way, yeah.
Yeah.
It essentially steals the oxygen away from the metal oxide, leaving the pure metal behind.
Sneaky carbon.
Well, it's a very useful reaction. It's called reduction, by the way, because the metal oxide loses oxygen.
Right, reduction is losing oxygen. But what about those metals higher up the reactivity series, the ones more reactive than carbon? Carbon can't really muscle in there, can it?
No, it can't. For those metals, like aluminium, sodium, potassium, we need a more powerful technique, electrolysis. It involves using electricity to break down the metal compound and get the pure metal. But it's more energy intensive, so we only use it for the really reactive metals where carbon can't do the job.
Okay, so electrolysis is like the big guns for metal extraction. We'll get to that later. But before we move on, let's talk about oxidation and reduction in a bit more detail. I remember this handy mnemonic, oil rig.
Ah, yes. Oil rig, oxidation is loss, reduction is gain. But it's not just about gaining or losing oxygen. It's about electrons, too.
Right, those tiny negatively charged particles we were talking about. So when a metal is oxidized, it's not just gaining oxygen, it's also losing electrons.
Exactly. And when it's reduced, it's gaining electrons. Think of it like this. Oxidation is like giving away your pocket money. You're losing something negative, electrons. Reduction is like receiving pocket money. You're getting something negative.
Okay, I think I'm getting that. So if we look at a chemical equation, how can we tell what's been oxidized and what's been reduced?
Well, you need to look at the changes in oxidation states. It's a way of keeping track of those electrons. For example, in the reaction of magnesium with hydrochloric acid to form magnesium chloride and hydrogen, the magnesium starts with an oxidation state of 0, because it's a pure element, and ends up with an oxidation state of +2 in magnesium chloride.
So its oxidation state increased, meaning it lost electrons.
Yes. And since oxidation is loss of electrons, magnesium has been oxidized. On the other hand, hydrogen starts with an oxidation state of +1 in hydrochloric acid and ends up with an oxidation state of 0 in hydrogen gas. Its oxidation state decreased, meaning it gained electrons and was reduced.
Got it. So it's all about tracking those electrons and seeing who's losing them, oxidation, and who's gaining them, reduction. Right, let's move on to acid reactions now. What are the key things we need to know about how acids react?
Well, first off, they react with some metals to produce a salt and hydrogen gas. Remember that magnesium and hydrochloric acid reaction? That's a classic example. It's also a redox reaction, by the way, like many reactions involving acids.
Redox again. So electrons are being transferred there too, right?
Absolutely. The magnesium is losing electrons, oxidation, and the hydrogen ions from the acid are gaining those electrons, reduction.
Okay, so acids react with some metals. What else do they react with?
They react with alkalis, which are soluble bases. Alkalis are metal hydroxides that dissolve in water, like sodium hydroxide, potassium hydroxide. When an acid reacts with an alkali, it forms a salt and water, a process called neutralisation.
So they sort of cancel each other out.
Yeah, you could say that. The acid's H+ ions react with the alkali's OH ions to form water, which is neutral.
Neat. And what about bases? How do they differ from alkalis?
Well, bases are a broader category. They include alkalis, but also insoluble metal hydroxides, like copper dihydroxide, and metal oxides, like magnesium oxide. They also react with acids to form salt and water.
So it's the same outcome, salt and water, whether it's an alkali or a base reacting with an acid.
Exactly. And acids also react with metal carbonates, like calcium carbonate, which you find in limestone, and marble.
Ah, yes, the classic vinegar and baking soda volcano experiment.
Yeah, that's a good example. When an acid reacts with a metal carbonate, it produces a salt, water, and carbon dioxide gas. That's what causes the fizzing.
So we've got acids reacting with metals, alkalis, bases, and carbonates. What determines the type of salt that's formed in each case?
It depends on the acid and the metal involved. For example, if you react hydrochloric acid with something, you'll always get a chloride salt. With nitric acid, you get a nitrate salt. And with sulfuric acid, you get a sulfate salt.
Okay, so the acid determines the type of salt. And what about the metal part of the salt?
That comes from the metal in the reactant. So if you react hydrochloric acid with sodium hydroxide, you get sodium chloride. If you react sulfuric acid with magnesium oxide, you get magnesium sulfate.
Makes sense. Now, how would we actually make a soluble salt in the lab?
One common method is to react an acid with an excess of an insoluble base. You keep adding the base to the acid until no more reacts. Then you filter off the excess base, and you're left with a solution of the salt.
Okay, so we get rid of the leftover base, and we're left with a salty solution. What next?
We can then evaporate some of the water to make the solution more concentrated, and then leave it to cool. As it cools, crystals of the salt will start to form. That's called crystallization.
So it's a bit like making rock candy, except with salt instead of sugar.
Yeah, kind of. It's all about getting those salt molecules to arrange themselves into those beautiful crystal structures.
All right, let's talk about pH now. What exactly does pH tell us about an acid or alkali?
pH is a measure of how acidic or alkaline a solution is. It runs from 0 to 14, with 7 being neutral. Anything below 7 is acidic, and anything above 7 is alkaline.
So the lower the pH, the stronger the acid.
Yes, a lower pH means a higher concentration of hydrogen ions, H+, which makes the solution more acidic.
And alkalis have a high pH because they release hydroxide ions.
Exactly. And when an acid reacts with an alkali, the H+ ions react with the OH ions to form water, which is why it's called neutralization.
Right, they neutralize each other. Now, there's this thing called a titration, which I remember being a bit fiddly. What's it all about?
Titrations are a very precise way of measuring the volumes of acid and alkali needed to react completely with each other. You basically add one solution to the other drop by drop until the reaction is complete, which you can tell using an indicator that changes color.
So it's all about finding that perfect balance point.
Yes. And once you know the volumes, you can use some calculations to work out things like the concentration of the unknown solution.
Okay, so titrations are for precise measurement. Now, another thing that often confuses people is the difference between strong and weak acids. Can you explain that?
Sure. A strong acid is one that completely ionizes in water. That means all the acid molecules break apart into their ions, hydrogen ions, and the negative ion from the acid.
So a strong acid releases all its H+ ions when it's in water.
Yes, pretty much.
Much?
A weak acid, on the other hand, only partially ionizes. So only some of the acid molecules release H+ ions.
So it's not about how much acid you have, but how readily it releases those H+ ions.
Exactly. And the strength of an acid is different from its concentration. You can have a dilute solution of a strong acid, and it will still have a low pH. And you can have a concentrated solution of a weak acid, and it might have a higher pH than the dilute strong acid.
Right, so strength is about ionization, and concentration is about how much acid is dissolved. Okay, I think I'm getting that. Let's move on to our final topic for today, electrolysis. Sounds a bit sci-fi, doesn't it?
It does a bit, but it's actually a pretty straightforward process. It's all about using electricity to break down compounds into simpler substances.
So it's like using electricity as a chemical wrecking ball.
In a way, yes, but it only works on molten or dissolved ionic compounds, where the ions are free to move about.
Why is that?
Because for electrolysis to work, the ions need to be able to carry the electric current. They can't do that if they're stuck in a solid. So we melt the compound or dissolve it in water to free up those ions.
Okay, so we've got our molten or dissolved ionic compound. What happens next?
We stick 2 electrodes into the compound, a positive electrode called the anode, and a negative electrode called the cathode, and we pass an electric current through them.
And this current causes the compound to break down.
Exactly. The positive ions in the compound, cations, are attracted to the negative cathode, where they gain electrons and are reduced. The negative ions, anions, are attracted to the positive anode, where they lose electrons and are oxidized.
So it's like a chemical sorting system with the positive ions going one way and the negative ions going the other.
Yeah, you could say that. And at each electrode, we see a chemical reaction happening, either reduction, gaining electrons, or oxidation, losing electrons.
What happens if we electrolyze a simple molten ionic compound, like lead bromide?
In that case, you'd get lead metal forming at the cathode and bromine gas forming at the anode. It's a pretty neat way of separating the elements in a compound.
Sounds straightforward enough, but how is electrolysis used in the real world?
Oh, it's used for loads of things. For example, it's used to extract very reactive metals from their ores, like aluminium.
Right, because we can't use carbon to extract those metals, as we discussed earlier.
Exactly. So we electrolyze the molten aluminium oxide, and we get pure aluminium at the cathode. But it's an energy-intensive process, so we have to use a lot of electricity.
Makes sense. What about electrolyzing solutions where the ionic compound is dissolved in water? Does that work the same way?
It's similar, but there's an added complication. When you electrolyze a solution, you have the ions from the compound, but you also have hydrogen ions and hydroxide ions from the water itself.
So there's more competition for who gets to react at the electrodes.
Exactly. At the cathode, hydrogen gas will be produced if the metal in the compound is more reactive than hydrogen. If the metal is less reactive than hydrogen, then the metal itself will be deposited on the cathode.
So it's like a chemical popularity contest with the less reactive metal winning the prize.
That's a good way of putting it. And at the anode, if there are halide ions present, chloride, bromide, or iodide, then one of those will usually be discharged, forming the corresponding halogen. If there are no halide ions, then oxygen gas is formed from the breakdown of water.
Right, so halides get priority if they're there, otherwise it's oxygen's turn. Now, I remember seeing these things called half equations for electrolysis. What are those all about?
Half equations show the individual reactions happening at each electrode. They focus on either the reduction reaction at the cathode or the oxidation reaction of the anode, making it clear what's gaining electrons and what's losing them.
So it's like zooming in on each electrode and seeing the electron transfer up close.
Precisely. They're really useful for understanding the details of what's going on during electrolysis.
Well, we've covered a lot of ground today. From reactivity series to acid reactions to electrolysis, it feels like we've explored a whole world of chemical changes.
We have. And it's all connected, really. These fundamental ideas of electron transfer, oxidation, or reduction, and the behavior of ions in solutions underpin so much of chemistry.
It's amazing to think that these concepts we're learning about in GCSE chemistry are actually the foundation for so many things in the world around us. From how metals are extracted, to how batteries work, to how industrial processes operate. It's all about understanding how matter behaves at its most basic level.
Absolutely. And I'd like to leave you with this thought. Think about how these principles might be applied in even more advanced ways. For example, how can our understanding of reactivity help us design better catalysts for chemical reactions? Or how can we use electrolysis to develop new and innovative ways of storing energy? These are just a few examples of how the concepts we've discussed today have far-reaching implications.
Fantastic food for thought. And if you're feeling inspired, I'd recommend revisiting your notes and maybe trying some practice questions to really solidify your understanding. Thanks for joining us for this deep dive into chemical changes.